Hey, just wanted to talk to you about section 1.3 and talk through some of the notes. So again, there are three different ways that we can find the limit of a function. So the first way was numerically. That's where we wrote a table out of x values that got closer and closer to our c value, or a given value that we were looking for, and just tried to see what happened with the function as it approached that c value. Second way was to look at it graphically. So we had a graph and we could see, oh, look, this function as x is approaching 2, this function approaches 7 or something like that. And again, historically, these would have been the more intuitive ways that we would have done that. But eventually we got to this evaluating limits analytically. And so again, we're going to mostly do analytically from now on. Okay, so we learned in section 1.2 that the limit of f of x as x approaches c does not depend on the value of f at c. Again, we had examples where if this was the function, and maybe it was undefined there, we could say that the limit, and again, let's pretend that's 3 and that's 1. We could say that even though the function is undefined at 1, that the limit still exists and it equals 3. All right, so when it's saying that the limit does not depend on the value at c, because again, here it's undefined, but the limit does exist and it's 3. Right? It may happen that the limit is f of c. Again, maybe this hollow dot wasn't there and it was filled in. And then the limit as x approached 1 in either direction would be c, and the value of the function at 1 would be 3. So it's possible that the limit is equal to f of c. When that happens, the limit can be evaluated by direct substitution. That means just literally plugging the x value into the function and seeing what you get out, right? In other words, the limit of the function as x approaches c is exactly the same as if you had just plugged c into the function, right? Doesn't happen all the time, but when it does, we celebrate. So here it says this well-behaved function. Again, if that happens, we're really happy because it's a nice function. This well-behaved function is said to be continuous at c. And again, this idea of continuity is that you can draw the curve without ever picking up your pencil, right? You're not looking at something like this where you've got to pick it up and because there's a break, or maybe say something like this where we have to pick it up because there's a hole and it hops over it. So when we say that the function is just really nice, again, think about something smooth and flowing, and that we don't ever have to pick up our pencil for. All right, so functions where this happens, we would say it's at least continuous at that point. Okay, again, as we start each new thing, we're going to end up with where we've got to kind of have these building blocks that tell us how to get to the good stuff. So there's going to be just a couple here that we're going to use. These are the foundational things that are going to help us analyze functions that are much more difficult. These are the building blocks. So it's saying that if we have a function that is actually just a constant function, imagine that it's f of x equals 2. All right, so b is just 2. Because again, this is usually where we put the name of the function, f of x, and so here it's some constant like 2. Because again, it's telling us let b and c be real numbers and let n be a positive integer. All right, so if we've got some function that's just a constant function and we want to see what the limit is of the function as x is approaching c, again, c is going to be right down here, and let's say this is b because it's our y value and it's a constant, right? So it's saying as x is approaching c from the left, as x is approaching c from the right, the function is always this constant value b, and so the limit would then be b. All right, so as we approach from the left, as we approach from the right, we're staying constant. I should say this, as we're approaching c from the left, as we're approaching c from the right, the function is staying constant at b. All right, so the limit of a constant is that constant. All right, if we just have something so basic as the function f of x equals x, right, that's just a linear function, has a slope of 1, and it goes through the origin as its y-intercept. Right, and again, we pick this value c right here. Again, what do we know about the function y equals x, or f of x equals x? Well, whatever I put in for x, since I'm not doing anything to it, Whatever I put in for x is what I get out for y. So if I put in 2 for x, I get out 2 for y. If I put in 7 for x, I get 7 for y. If I put in -10 for x, I get -10 for y. They match. The x and y coordinates are the same. So it's saying as I approach c on the x-axis, the function is approaching c on the y-axis. All right, so the y value is also approaching c because of the fact that x and y match when we're talking about this function. All right, so hopefully that makes sense because of the nature of this function, that it's just y equals x, that whenever I approach a c on the x-axis, or in the x values, that the y values will approach that same value, or the function will approach that same value because x and y are equal in this function. Okay, and then the final building block is, suppose now I have something to a power. So again, think about all functions that we know, linear functions, y equals ax plus b. Or first, let's just say a constant function, y equals b. Then we move up to linear, y equals ax plus b. And then we talk about quadratic, y equals ax squared plus bx plus c. Watch what's happening. The first thing, well, the first case we dealt with was this, right? Again, that's our constant function. The second thing is we said, oh, okay, well, we know what to do with a constant function. Let's talk about the x part, all right? How do we take the limit of that next block? And then the third hurdle to cross is what happens when we start doing powers of things. So again, a cubic or a quadratic would be ax squared plus bx plus c. The next we would run into is ax cubed plus bx plus cx plus d. So again, this is the next part. How do we deal with exponents? Right? Well, it's just saying that if we have some x to the nth power, so let's say an x squared, again, this is a nice function. There's nothing weird that happens with it, right? It's a quadratic, it's a cubic, it's something like that, where we were using this word continuous, where we just get to draw it without picking up our pencil. And in this case, we just say that it's that number that we're approaching to the same nth power, right? So again, let's imagine that it's x squared. And we've got this, let's say, like that. And we approach some number, let's say 2, right? As we approach 2, right here, either from the left or from the right, the function is approaching 2 squared or 4. All right, and so we would just say it's whatever that c value was. In this case, I just randomly picked 2. It's c to that same power of n. Okay, hopefully you feel okay about that. Let's look down here. So now let's start applying them. Let's use, again, we're going to do one exactly like this, one exactly like this, and one exactly like this. And then down here, we will start adding more levels of difficulty. Because again, all we dealt with was the x squared here. What happens if it's an ax squared? How does that change the limit, right? So here it's saying we've got the function f of x equals 3 or y equals 3. And what happens as x is approaching 2? All right, so here's 1, 2, 3. We've got this line right there. And it says x is approaching 2. 1, 2. All right, so as the x values are approaching 2 from the left and from the right, this function stays a constant 3. All right, and again, that's exactly what this said would happen. That if we're taking the limit of a constant, it's just going to stay that same value. And that's exactly what happened here. All right, here, same thing. We've got the line y equals x. So again, it's got a slope 1. It's going to cross through the origin. And it's asking, as we approach -4 on the x-axis, what's happening on the function? So as we approach at -4 here from either the left or the right, what's happening with the function? Well, it's getting closer and closer to -4. So this, it's telling us if we have the limit of the function x, it's just going to equal the value that we're approaching, c. And that's exactly what happened here. And then same thing, wow, I didn't even notice that that's what it was. But here, if the function is x squared, just as I drew up here, and we're approaching 2 from the left or from the right, what's happening to the curve? Well, it's approaching 2 squared or 4. Okay, now These are just a bunch of rules that we would hope would be true. It's saying let B and C be real numbers, let n be a positive integer, let f and g be functions with the following limits. So it's saying that the limit of the function f as x approaches c is some number L, and there's a different function g of x, it's also approaching c, and its limit is k. So imagine we have something like this. I don't know, we've got c right here, and let's say that this is the function f, and let's say this is the function g. All right, so as x approaches c on the function f, we would say that's the limit, and we're going to call that L. And on g, that is the value k right here. All right, so that's what they mean. We have two separate functions. As x approaches c, f approaches L, whatever that is, and as x approaches c, g of x approaches this value k. All right, so this one is saying that if we were to take some scalar multiple of the function, again, if I've got this function, let's say x squared plus 2, a scalar multiple would just take a constant out front like -5 and multiply it through. All right, and again, we know from our work with quadratics that that's going to cause it to either stretch or compress, right? And what it's telling us is that the limit of the product is the same as the product of the limits. So again, if we broke this up into the limit as x approaches c of b times the limit as x approaches c of f of x, this is a constant, and we know that's b. And then this is the limit of our function, which we defined as L. Right? So it's just saying that the limit of a product is the product of the limits. Right? This one says something similar, that the limit of the sum or difference is the sum or difference of the limits. All right, so we could say that this is the same thing as the limit of f of x as x approaches c. I'll just do plus. All right, you could do the same thing with minus. Is the same thing as the limit of f of x as x approaches c plus the limit of g of x as x approaches c. Well, what is the limit of f of x as x approaches c? It's just L. And then the limit of g of x as x approaches c is just k. All right, so the limit of the sum is the same as the sum of the limits. All right, likewise, we could say the same thing about a product. All right, so if I have a product of two functions, all right, that's very similar to up here, except one of them was a constant. So it's saying if I have a product of two separate functions that are not constant, it's the same thing. The limit of the product is the same as the product of the limits. So again, if I broke that apart into limit of f of x as x approaches c, I'm running out of room here, times the limit of g of x as x approaches c, limit of f of x is L, and the limit of g of x is k, and that's exactly what we got. All right, this one has a little qualifier. It's the same thing here. It's saying the limit of a quotient is the same thing as the quotient of the limits. But we have this caveat right here. We have to make sure that k, that limit of the function g, is not equal to 0. If it is equal to 0, this fails. All right, so as long as what we're approaching, as long as what g is approaching as x is approaching z is not equal to 0, then this is true. Again, if you remember that function that we looked at, x cubed minus 1 over x minus 1, if we took the limit as x approaches 1, we're out of luck, because this would end up being 1 minus 1, which would approach 0. So it's saying as long as we don't choose, or as long as the value of x does not make the denominator 0, then we're fine. If it does, then we're going to have to talk about some other strategy. Okay, and then finally, this power rule, saying that if I have the limit of f of x to some power, that's the same thing as doing the limit of f of x as x approaches c, and then taking that power. All right. So the limit of a power is the power of the limit. All right. And we know that this is just L. So this is L to the n. So everything that we would hope to be true about limits, this is saying is true. We would hope that we could multiply a function by something and just get that same multiple of a limit. All right. Just like here, if I had 3x squared, I would hope that I could just take the limit of x squared and then multiply it by 3, right? And it's saying, yeah, actually that's true, right? It's hoping that if I take the sum of two things, like 3x squared plus 5x, this would be like our f and our g, that I can just take the limit of this and the limit of this and add them together. And again, that's what this is saying right here. So everything that we would like to be true about limits in terms of combining these basic building blocks, this is telling us is actually true. All right, so let's find the limit of this. Again, we will never do the limits the way I'm doing it right now, but I just want you to see how these rules work. So I'm going to be a little bit uptight about it right here, but again, we won't ever do it this way in real life. All right, so we're just going to apply these. All right, so first we have a sum of 4x squared and 3. All right, so that would be a sum or difference. So what that tells us is that if I have a limit of a sum, I can rewrite this as the limit of 4x squared as x approaches 2 plus the limit of 3 as x approaches 2. So again, the limit of a sum is the sum of the two limits. All right, now let's take this one. Actually, let me just write here, this is the sum and difference rule. All right, let's take the next one. This right here, again, remember that in our building block, we just talked about this, some power with no coefficient in front of it. So now we have this power right here, but it has a 4 in front of it. So what we learned from the scalar multiple says that if I have some just constant coefficient in the front, not a variable in there, but just some real number times our function, like we do here, we have 4 times our x squared, that we can rewrite it as 4 times the limit of x squared as x approaches 2, right, plus the limit as x approaches 3. So we're just gonna, as x approaches 2 of the function 3. So we're just gonna deal with this one. That's the scalar multiple. All right, and then next we're going to just apply the ones that we have. So this now is one of those very basic building blocks. So it says if we have x to some power n, here it's x to the second power, that we could just directly substitute into here. So this is going to be 4 times 2 squared. I'm just directly evaluating here. And this one tells us that the limit is just going to be the constant 3. All right, and I'm just going to call these basic limits. And the reason I'm calling them basic limits is because that's what we called them up here, basic limits. Those are our 3 building blocks. Okay, and now I'm just going to do that. So 4 times 2 squared would be 16, and then 16 plus 3, so we would get 19 as the limit. All right, let me show you one more thing. Well, lots of things, but all right. So note that the limit of the function p of x, which is what we're calling this 4x squared plus 3. Note that the limit of p of x is just the same thing, or as x approaches 2, is just the same thing as evaluating the function at 2. All right, it's just p of 2. All right, and then we have the note here that this direct substitution property is valid for all polynomials. So again, any polynomials, quadratic, linear, cubic, quartic, and it's valid also anytime we have a rational function as long as the denominator is not 0. Again, that does not apply with that example that we looked at with some degree of thoroughness, where I cannot use this direct substitution here if I take the limit as x is approaching 1, because it makes the denominator 0. All right, so I can use rational. Now, if we were to do the same thing again, but using x equals, say, something like 2, the limit of x cubed minus 1 over x minus 1 as x is approaching 2. Again, now because if I put 2 in the denominator and I don't get 0, I can just do this limit by direct substitution. So we would end up with 2 cubed, or 8, minus 1 over 2 minus 1, which ends up giving us 7. All right, so again, polynomials are all fine, and as long as the denominator is not made 0 by substituting in our the c value that we get. So in a situation like this, a rational function is fine, but here where we put 1 in or some other c value and we get 0 in the denominator, we can't do that. All right, so then we need to, in a minute, we're going to talk about other strategies that we can use. Okay, so here is, we're just saying this very generally, here we're making it official. All right, so if p is a polynomial function and c is a real number, then the limit of the polynomial function as x approaches c is just the same as directly evaluating, or in other words, plugging that value in. All right, so as long as it's polynomial, we can just do direct substitution. And again, formally, we're saying here, if r is a rational function, meaning it's a polynomial over polynomial, so if it's r is a rational function given by p of x, some polynomial, over q of x, some other polynomial, and c is a real number, so that when we plug c into the denominator, we do not get 0, then the limit of the rational function r as x approaches c is the same as substituting c into the rational function, in other words, substituting it into the numerator and to the denominator. All right, so here we're just formalizing what we noted up here. All right, so for example, they're saying, let's find the limit of a rational function here. And so first we're going to note, right, that when we plug 1 into the denominator, so that, let's call that maybe, well, let's just say that when we do 1 plus 1, we don't get 0. All right, so then we can use this theorem 1.3 says that we can use this. So we can apply theorem 1.3. And so the limit as x approaches 1 of the function x squared plus x plus 2 over x plus 1 is just the same as plugging in 1 for x. So 1 squared plus 1 plus 2 over 1 plus 1. In other words, 4 over 2, which is 2. Right, again, before we would have done a table, all right, so we might have chosen values like 0.9, 0.99, 0.999, values that approach 1 from the left, and then we might have chosen 1.001, 1.01, 1.1, values coming in from the right. But here we can just directly substitute it in there. Okay, let's take a look at what happens when we end up with a radical. So again, we're just building up different types of algebraic functions here. All right, so let n be a positive integer. So again, maybe it's like 3 or 7. So here we're talking about the cube root, the 7th root, something like that. All right, then the following limit is valid for all values of c if n is odd. All right, so think about that. If that's 3, so maybe cube root, we can put any c value in here that we want. And it's only valid for values of c greater than 0 if n is even. Right, so if we have the square root, let's say, we have to put a positive value in there. All right, so then what it's saying is if we've got these conditions, either n is odd and we use any c value, or if n is even and we pick a c value that's greater than 0, then the limit of a radical is just the same as plugging the value of c into the radical. Okay, so again, direct substitution here works when we have either an odd index, any c, or if it's an even index and we have a c positive. Okay, there is a typo on your sheet, which I will correct. Maybe I have already corrected it by the time you watch this, but this should say if f and g are functions such that not f of x, I don't know what I was thinking when I typed this up, such as the limit as x approaches c of some function g of x is equal to L. So g has a limit and it's L as x approaches c. And the limit of the function f as x approaches c is f of L, right? So here's some function that has a limit L, and then the limit of f of x as x approaches that same c value is just L plugged into f, right? So then it's saying that if we have the composition of functions, the limit as x approaches c of f of g of x is the same as f of the limit of g of x, which we know to be L, right? And they're saying it's f of L. Again, think about when we've done composition of functions before. We've got some rule, g, let's say, that takes a value right here and maps it over to here. So let's say that value is c and it maps it over to L. And then when we take f, the limit of f as we're going over here, all right, then we would put that in, whoops, not capital F, just lowercase, and then we would get f of L, right? So we're taking the c value and then we're applying g to it, and then we're basically applying f to this right here, and we get f of L, right? So that's what composition of function is doing, and it's saying that same thing applies with limits, right? So in example 4 here, we have got a function f of x equals the square root of x, and g of x equals x squared plus 4. And there's things here that I did not write. Again, I need to correct that. So f is going to be the outer function. G is the inner function. Okay, just like up here that we just talked about, f is the outer, g is the inner, so we're going to assume the same thing here. And we are going to note that as x is approaching 0, again, I don't know why I forgot to do this, so we're going to look as x is approaching 0. So we take this and we're going to say, all right, the limit as x approaches 0 of g of x, which is x squared plus 4, is 4. And then we're going to say that the limit as x approaches 0 of f of g of x, all right, so that's going to look like the limit as x approaches 0 of now not just this, but now we're applying the square root to it, is just going to be the square root, again, that's what the outer function is, the square root of 4, which is what we got right here, right? And then we would say it's 2. All right, so if we know what the inner function is, when we take the limit as x approaches 0, we would say that it's 4. And then when we take the limit of the composition of the function, again, it's just like taking the outer function, that square root, and just putting the value that we got for the inner function inside of it. And so we end up getting 2. All right, hopefully you're following along what's going there. So it's, again, it's saying that we can just take the limit, that we can just take f of the limit of the inside to get that outer value. Okay, and then we can do the same thing here. So again, f is the outer, g is the inner. And again, I don't know why I did not write these things down, but we're going to take the limit as x approaches 3 of our inner function, g of x, right, which is this. So we're going to take the limit of g of x, which again is the limit of 2x squared minus 10 as x approaches 3. All right, And so what we're saying then is as x approaches 3, we can just do direct substitution. This is a polynomial. So we get 3 squared, which is 9, times 2 is 18, minus 10, and we end up with 8. Right? What it's saying now is if we're trying to find the limit of the composition, f of g of x, as x approaches 3, that we can just do f of the limit of the inside. We'll do both just so that you can see that it is the same. So one way is we can find f of g of x, which is, again, I'm sorry, I always go too low on these, the cube root of 2x squared minus 10. So one way would be to go this way, where we actually find f of g of x and take the limit of it. So we can just do direct substitution here. If I plug in 3 into here, I just found out that I get 8. So then it's the limit as x approaches 3 of the cube root of 8, which is 2. And again, using that theorem 1.5, it's saying it's also true that it is just f of the limit of g of x. All right, the limit of g of x we just found was 8. And f of 8 is the cube root of 8, which is 2. All right, so it's telling us that we can do either way, that we can find f of g and then take the limit, or it's saying just take the limit of the inner function and then take f of that. All right, so either way we end up with 2. Okay, let's just talk about these really quickly. And the thing that I want to emphasize here is in theorem 1.6, the limit of trig functions, let C be a real number. Okay, that's fine. In the domain of the given trig function. And again, you've taken trig, and so you should know these, but again, it might be a while, so let's just talk about them. The domain of sine is all real numbers. So for sine, the domain is all real numbers. For cosine, domain is all real numbers. For tangent, all right, the domain, so let's just stop with there. This is all real numbers. For the tangent, we cannot include anything that's of the form pi plus or minus, pi over 2 plus or minus pi n. So any, we start at pi over 2, and then every pi after that that we add to it also gives us something that's not in its domain. So here, this is the domain, and here we exclude these from the domain. All right, so nothing is excluded here. Domain is all real, but this, the remaining 4 functions do have different things where there is no, where we can't choose them. So in tangent, we cannot use pi over 2 plus integer multiples of pi. All right, cotangent is just going to be plus or minus pi n. So again, this would be pi, 2 pi, 3 pi, 4 pi, negative 10 pi, negative 12 pi. So integer multiples of pi. This is all going to be, if we write this out, let me do that down here. This is pi over 2 plus pi. This is pi over 2 plus 2 pi, pi over 2 plus 3 pi. Right, if I find a common denominator, this ends up being 3 pi over 2. I find a common denominator, this ends up being 5 pi over 2. I find a common denominator, this ends up being 7 pi over 2. So it's all pi over 2's with an odd numerator, basically, is what this is. This is all integer multiples of pi. All right, and then secant is exactly the same as tangent. Again, if you think about this, tangent is sine over cosine. So really what we're looking for is where is cosine 0? That's what makes this things that are no longer in the domain of tangent. Secant is 1 over cosine. So again, it's that same thing. These are going to have the same problems with their domain. So this is also going to be pi over 2 plus or minus pi n. right? Cotangent is cosine over sine. So these values here are everywhere that sine is 0. That's why it's excluded from the domain, because sine is in the denominator. So again, cosecant, same thing. It's just going to be plus or minus pi n, because this is 1 over sine. So again, sine is in the denominator. We're looking for where the sine is 0, because we're saying that is where that function's undefined, right? So it's saying, yeah, go ahead and plug in anything you want into this. You can do direct substitution as long as it's in the domain. So for sine and cosine, everything is domain. It's fine. But for tangent, cotangent, secant, and cosecant, you must be careful. You must make sure for tangent and secant, you're not picking an odd, a pi over 2 with an odd coefficient up top. And for cotangent and cosecant, you cannot pick any integer multiples of pi. Okay, so let's then find, let's apply this theorem right here, so that we can see what we get right here. So limit of tangent of x as x approaches 0. So again, we say we are totally allowed to do direct substitution as long as 0 is part of the domain of tangent. And again, for tangent, we're avoiding things that are pi over 2, odd multiples of pi over 2, basically. When we look at this pattern here, odd multiples of pi over 2. That is not one of them. All right, this is an even multiple of pi over 2 because it's 0 times pi over 2, right? So that says we can just substitute it in directly, right? So tangent of 0 is what it's telling us this is equal to. All right, and again, hopefully you remember that tangent of 0 is just equal to 0. Right, you could use your unit circle. You could say, oh, I know it's sine of 0 over cosine of 0. I know sine of 0 is 0 and cosine of 0 is 1, therefore it's 1. Whatever method you need to use to remember, whoops, not 1, 0. Whatever method you need to do to remember that tangent of 0 is 0, that's fine. Okay, the next one, part B. Cosine, the limit as x times cosine x, let me say that again. The limit of x times cosine x as x is approaching pi. Right, so here our function is cosine x, and then we also have this polynomial that's being multiplied by it, right? So direct substitution is fine for polynomials, and it's also fine for cosine of x. Again, domain is all real numbers here. So we're just going to plug in pi through direct substitution. So we write pi, because we're just substituting that in for x, times cosine of pi. All right, so then we end up with pi. Cosine of pi, if you remember, pi is at the coordinates -1, 0, and cosine is always the x coordinate, so here it's -1, and so we end up with negative pi. Okay, and then right here, we've got, again, a sine function. Really, this is the same thing as limit as x approaches 0 of sine x quantity squared, which again we know from some of our earlier rules that we talked about, that we can just say that this is limit as x approaches 0 of sine x squared. Again, this is like our composition of functions here, that we have sine x as our g, our inner function, and x squared as our outer function. And so it's saying we can do our inner function, find out what the limit is, and then apply the outer function. All right, so as x approaches 0, sine is equal to 0, and then we just end up applying the outer function, whoops, not 0, 2, and so we end up with 0. All right, again, this part, seriously, keep that written somewhere handy, because you're going to need this frequently as we do these. So just have some record here that the domain for sine and cosine is all real. The domain for tangent, cotangent, secant, and cosecant is all reals minus these things right here. Right, so these are the things that are not included in the domain. So it's all reals except for these. It's still a pretty big area. All right, so we've got to be careful because there are many occurrences of asymptotes there.